Yes, so welcome to the last talk of the day. We have Bryce here from MIT, USA, and he's going to talk about CMB spectral distortions, the what, how, and when. Maybe I'll send you a reminder when 5 minutes are left.
Yeah, sounds good. Okay, thank you very much for the invitation to talk in this, I guess, Italian Indian seminar series, which seems to have a lot of really great speakers. So I'm really happy to be part of it. I'm going to talk kind of about a little bit more of a broad scoped discussion on these things that I find extremely cool called CMB spectral distortions. Please interrupt me at any point if you have a question or a clarification, or also if my Wi-Fi is a bit choppy, let me know because it's a hotel, so you never know what's going to happen. All right, so the outline of this talk is to kind of go through these three, I guess, statements that I made in the title, the what, the how, and the when. So the what will be describing really the science behind what these CMB spectral distortions are. I'll talk about the current state of the art in terms of measurements of these things. You'll be very disappointed by that part, and you will see it does not take very long to get through it. Then I will tell you how these spectral distortions could be generated and why essentially it's exciting to try and look for these things. But I think the part of the talk that I'm most excited to be able to have is this experimental timelines part. So I'm a theorist, but there has really never been a moment quite like right now where experiments are actually starting to try and detect what I think is an extremely cool piece of physics. So I'll happily share the updates from a theorist perspective on what these experiments are doing and when we might hope to be able to start constraining some truly fundamental physics. So to start, I always have to introduce what I mean by spectral distortions, because usually when people think of the cosmic microwave background, they're thinking of that, beautiful picture that you've seen from Planck, that looks like the static of the universe, essentially. That's the temperature anisotropy map. This is something different. This is the frequency spectrum of the cosmic microwave background itself. So instead of looking point to point on the sky, and measuring an effective temperature along each line of sight, what you do for this measurement is you literally just collect every single CMB photon that exists in the universe over the entire sky, and you put it into a histogram of frequency versus intensity. And you can see that the data points are given by these dots with error bars. And then afterwards, because we're physicists, after all, we want to fit this data to something, you fit it to a perfect black body curve. So that's this intensity as a function of nu right here. This is a perfect Planckian distribution. It's described simply by one parameter, the temperature. And you find beautifully that this theory curve goes perfectly through the data points. Okay, so this was an experiment done in the 90s called the Kobe-Firis satellite. It's kind of the first of the three CMB anisotropy-esque satellites. So Kobe-Firis was one, WMAP and Planck are the other two. And back in the days of the 90s, they had much stricter standards for what was acceptable to put on a plot. So here the error bars you see are at 400 sigma. So none of this 5 sigma stuff that LHC talks about. I mean, cosmology back in the day was all about 400 sigma. Of course, I'm not being serious. This is just for propaganda purposes to show how perfect of a fit the black body spectrum is to the data points itself. So this is the measurement that told us that the temperature of the universe is 2.7 degrees Kelvin. Has had a lot of profound implications, and in some sense, the temperature of the universe is the seventh lambda CDM parameter that's not really talked about very much. But even to this day, this is the most perfect black body that we have ever measured in nature. So to be able to have done this in the 90s is really phenomenal. And this measurement has stood the test of time in many different respects that you'll see as I go through my slides. But if you're like me, you're kind of deeply unsatisfied with life in general, and that extends to science. So you're always asking the question, well, how perfect is it actually? And I'm not the only person in science who's dissatisfied, so other people have done this before. And you find that if you were to look for the level of deviations away from this theory curve in the data, you would find that the deviations must be at a level of 10 to the negative 5 or less. So one part in 10 to the 5, the data perfectly matches the theory. If you want to translate this into what I would kind of call more coarse-grained spectral parameters that I'll give you a bit more intuition for in the following slides, you can do that. And we typically in distortion science refer to two types of spectral distortion parameters. One is the mu-type distortion, which usually governs very early physics, very pre-recombination. And the other is the Y-type distortion parameter. So these are both constrained from Kobe-Virus back in the 90s at roughly the same level as this delta I over I. This is not a coincidence. These things are closely related. But you may have noticed that it's not 1996 anymore. It's not even 2006 or 2016. It's 2026. So it's been 30 years since this measurement was taken. So you're probably asking me, okay, well, what do we see now? This was beautiful back then. What do we get now? And I'm sorry to disappoint you, but these are still the most recent results that we have for for the spectrum of the cosmic microwave background. So this measurement has never been done since then, and that's a shame for many reasons. I mean, our understanding of the universe has transformed hugely since then, and technology has increased hugely since then. And so people who work on experiments have thought about and written white papers on proposed next generation satellites that could fly. And the sensitivity that you would expect from these next generation satellites is orders of magnitude better than what was done back in the 90s, as one might expect after 30 years. So just to put into some context, many experiments in cosmology are kind of proposed and funded based on factors of two or factors of five or an order of magnitude improvement. Multiple orders of magnitude is truly unheard of, and the science that you can gain from this type of sensitivity increase is also something that I personally believe would transform a lot of our understanding of, particularly the pre-recombination universe. Okay, but you can also reasonably ask the question, Bryce, I know the universe was extremely hot and extremely dense at these early times. Thermalization is a very efficient process, I thought. So why would I ever expect anything other than a black body? And those are all somewhat true statements. So the maybe one sentence summary of what spectral distortions, so deviations away from a perfect black body shape of the CMB spectrum would tell us is they would tell us information about non-thermal injections or extractions of energy. So say you inject a bunch of electrons, that would be an energy dump, or entropy, so direct photon injection at many different times in the early universe. Okay. And as you will see in a second, there in fact are standard model signals that we expect, predicted by inflation, that we can and should be trying to test. So probably the most famous signature of a spectral distortion that's truly primordial is a mu-type distortion at the level of 2 times 10 to the negative 8, which is certainly in reach of these current generation satellites that are being proposed. So this is a clear target for us to search for. And in searching for that target, there is a huge amount of beyond the standard model scenarios that you can constrain. There are many scenarios that are still constrained at leading order by the Kobe-Fire satellite, which is 30 years old. So you get 3 orders of magnitude improvement here. You get massive improvement in the constraints or maybe even detections of some of these scenarios. Okay, so if you wanted to open up that question of, well, Bryce, I thought the universe was very hot and dense and thermalization is efficient, I have to remind you of your thermodynamics 101 classes, which is to answer that question. If I have some type of a non-thermal deviation from a black body, how does it get thermalized again? How does it go back to a black body shape? So imagine again, I have this type of a spectrum, like a black body. And just for the purposes of this example, imagine that I inject a spike of photons right around the peak, and I inject that spike at different redshifts. What will it look like today? How will that spike get kind of smeared out over the rest of the CMB spectrum, and will it go back to a black body or not? So in order to answer this question, you need to remember that if I want to have true thermal equilibrium, two things need to be very, very efficient in the early universe. You need to be able to redistribute energy across the spectrum, of course, and you also need to be able to create and destroy photons at will. Okay, so a black body spectrum is a delicate balance between the total energy density of your backgrounds and the total number density of the photons. So both of these things are required in order to go back to a Planckian spectrum. But cosmology is also very kind to us, right? Because the universe is expanding, which means that interactions, governed by this gamma here, that would have been very efficient at high redshifts, will freeze out at late times and become inefficient. As the universe expands, things just literally become farther apart from each other. The typical energies of species as they collide also goes down. And so these interactions that could mediate thermality early on will become inefficient at some point. In the standard model, only standard model, the things that mediate this at lowest order are these three processes. So Compton scattering gives you a way to efficiently exchange energy across the spectrum. And then double Compton scattering and Bremsstrahlung are able to produce and destroy the new photons to properly regulate you returning to a black body. So if I was to inject that temperature or that spike in the CMB spectrum at a redshift above 10 to the 6, if you prefer ambient temperatures of the universe, basically above keV, then it turns out that all of these processes are completely efficient, and as a result, the resulting spectral distortion is that there is none. You will just go back to another perfect black body. In practice, what happens is this injection of energy raises the temperature of the CMB, so your temperature does go up, but we don't have an a priori prediction for what TCMB actually should be, right? It's not something that we can use to constrain models. It's not an observable in some sense. And so if you inject energy above this redshift, you kind of are insensitive to these spectral distortions. But this is still a very high redshift. And if you go below this redshift, so at redshifts between 5 times 10 to the 4 and 10 to the 6, you produce what is known as the mu-type spectral distortion. So this happens, and there's a very clean picture as to why this happens. So when these number changing interactions freeze out, become inefficient, if you solve the photon-Boltzmann equation in the presence of a collision term given just by Compton scattering, then it turns out that the steady state solution to that equation is no longer this black body Planckian spectrum, but is actually a Bose-Einstein solution. And if you know anything from statistical mechanics, you know that the Planckian distribution is described by one parameter, the temperature, but a Bose-Einstein distribution is described by two things, which is a temperature and a chemical potential, which is usually given by this mu symbol. So this is why we call it the mu distortion era. Injection of energy at that point in time will lead to a small chemical potential in the plasma that is a spectral distortion that you can go and hunt for. If you inject that energy at even lower redshifts, then you produce what is known as a Y-type distortion. I don't really have time to go into exactly why it's called that. It has to do with the Sunyaev-Zeldovich effect, if people are aware and have studied that before. But just so you have it in the back of your head, it's another kind of general spectral template that you can use and you can search for in the data, which will constrain energy releases at these lower redshifts. So obviously, it's not a cosmology talk if you don't have a plot that looks kind of like this. You have the Big Bang on the left-hand side here, where inflation or some yet to be discovered alternative to inflation occurred, produces all of the fluctuations that we see in the universe today. For the first year of the universe's history, you're in this thermalization era where you're somewhat insensitive to spectral distortions. But then quite quickly, you transition to the mu distortion era. Okay, so remember the CMB forms at 380,000 years after the Big Bang, and it is notoriously hard to reconstruct information behind this veil of the CMB, but spectral distortions are, in my opinion, one of the best ways that we could actually hunt for this. So you have a mu distortion era, you have a Y distortion era. There are also things known as recombination lines that I'll describe in a moment that are extremely cool. But one thing that is very valuable that, if you've heard of spectral distortions before, you may have as a suspicion in the back of your head, is that there is also this mu-Y transition era. So of course, when interactions freeze out, they're not like Heaviside functions. They don't just Compton scattering doesn't just say, okay, I'm stopping now. It's a smooth process. And what that means is that if you have a spectral distortion that is generated in this mu-Y era, the actual distortion that you will detect today here on Earth will not just be a superposition of some mu-type spectrum and some Y-type spectrum. There will be additional residual information in the spectrum that you can use to fully characterize the time dependence of your energy release mechanism. So if you had, for example, a decaying dark matter model that you wanted to try and constrain, then you would be able to constrain the parameters of that lifetime based exactly on the injection history of this unstable dark matter candidate, for example. So this is an extremely powerful tool that allows you to do model discrimination with this type of data as well. So these are not just integrated constraints. Okay, so maybe let's just focus on the plot on the right here, just so that you get a picture of what a distortion actually looks like. If you think about a black body spectrum, the peak of the black body is around 200 gigahertz. So imagine a line that kind of goes through this temperature shift contour. This is a Green's function response, but in practice, you can think of this as there's a 0 point line that goes across flat here. And anytime the curve dips below the zero, it refers to a moment in which there is a decrement of photons relative to a black body spectrum, and every time it's above zero, there's an excess of photons relative to a black body spectrum. So each of these contours are doing this exact example that I mentioned to you a second ago. You take the black body spectrum, you inject some spike of energy at some point at a different redshift. Each contour corresponds to the spectral response you would see today at a different redshift. Okay. So it goes from the very highest redshifts, which would be this temperature shift curve, to redshifts, for example, to injections at redshift of, for example, 3 times 10 to the 5, which would be this blue mu distortion curve. And then this Y distortion curve would be an injection at the latest times of redshift of, let's say, recombination around redshift of 1,000. So typically you will always see this decrement for positive spectral distortions. You'll see this decrement of photons in the Rayleigh-Jeans tail and an excess in the Wien tail. And this just comes from the fact that if your number is conserved and you give extra energy to the spectrum, then you will upscatter the photons that were already in the Rayleigh-Jeans tail up into the Wien tail, and then you can search for this type of a thing. Yeah, so and then it's hard to see in this plot, but there is residual information when you start to inject basically at redshifts between this blue and this black curve. So this is what a distortion would look like in actual spectral data. Okay, obviously this is a very powerful probe, both of the standard model and exotic physics. As I kind of alluded to earlier, there is a lot of ways to disturb equilibrium. That's the nice thing about equilibrium is that anything that is not equilibrium will create a spectral distortion. So I think all of the things that are listed here I've worked on at some point, so I'm happy to answer questions about any of them either offline or later. But there are literally, as I said, hundreds of models that have some region of parameter space still constrained by Kobe fires, this old data, and just waiting to be detected by somebody who wants to build one of these satellites today. So in addition to these exotic scenarios, of course, the standard model can also be probed very sensitively. Silk damping is the process that I will tell you about in a second that produces a distortion that I'm very interested in. But reionization, so when the first stars start to turn on, their UV light basically heats up the gas, and that heating up of the gas will upscatter the CMB, which therefore leads to a distortion. So you can probe many of these important and difficult to see otherwise epochs in our thermal history, basically all the way from 1 year after the Big Bang until today. Um, and then the recombination lines, I think I'll show you a plot of what they look like in a second so I can describe that momentarily. Okay, so just to give you a flavor for this kind of, I don't know, maybe a smoking gun signature, I should say, of primordial mu distortion is something that comes from the silk damping procedure. So if you're unfamiliar, first of all, this plot I hope everybody has seen before. You know, this is the famous CMB temperature anisotropy plot from Planck, and then this curve in the plot is the power spectrum. So this is the 2-point correlation function Fourier transforms. On the far right-hand side of this axis, these large L's correspond to small angular scales, so 2 points that are closer and closer together. And on the left-hand side, the largest angular scales, and you see the classic acoustic oscillation features that we've detected and basically allow us to enjoy this age of precision cosmology with lambda CDM. But what you should notice is that all the way down here, there's not a lot of power, and all the way up here, there is a lot of power. So let's just think for a second about the physics of what actually happens that goes into what makes this plot, right? So if you think about the universe after inflation, every single patch can essentially be assigned its own temperature fluctuation, which is inherited from the quantum fluctuations generated during inflation. And as the universe continues to expand, these patches that were initially causally disconnected come into causal contact. And these slightly different temperature patches then mix and try and homogenize. So, electrons and photons in one patch that were slightly higher temperature enter a patch that was slightly lower temperature. They interact and they try and become a uniform temperature. So this is exactly why on small scales there's no power, is because those patches have already homogenized, and therefore you don't see a variation, let's say, when you start looking at 2 points extremely close together on this map. But when those modes initially entered the universe, they had a lot of power. I mean, there would have been a peak, something like this, if you were measuring the power spectrum at the moment these modes entered. So where does that power actually go? We like to think that energy is conserved in cosmology, at least most of the time. And the answer is that there's only really one place it can go. This energy gets dumped into the plasma itself. Um, so a toy model of how you can imagine this process is if I ask you a question, which is something the seminar speakers are never supposed to do, but I'm going to do anyway. And I ask you, what is the spectrum that you get if you sum two of these black body spectra, one with a temperature slightly lower than the mean, and one with a temperature slightly higher than the mean, and initially they're both complete black bodies. There's no spectral distortion whatsoever. So what happens if I add these two things together? And this is, yeah, somebody can answer if they want to. Usually people just look at me awkwardly, but now that I'm on Zoom, I can't see all the awkward faces. But I can hear the awkward silence, which is just as good. Um,
So assuming that it would still be a black body,
that's exactly what I wanted you to say because that's
uh,
exactly what it's not.
yeah.
So if you add these two things together, it actually turns out that this does not go to a black body after all. If you look at the energy density of this new patch that you've mixed together, it looks like something that is T to the 4, but there's some additional energy that is related to the fluctuation that existed in the initial two patches. So, in some sense, there is a memory associated with the energy density of the new patch that you've created. And in fact, depending on the redshift at which you mix these two patches, you will lead to either a mu-type distortion or a y-type distortion. So the earlier the patches mix, the more they can produce these mu-type distortions. At the very earliest times, you're not sensitive, but in the mu era, you certainly are. And if you do the not sloppy thing that I've done here, but you do the more sophisticated thing by adding up every single patch that comes into causal contact between redshifts of roughly 10 to the 4 and 10 to the 6, you find that the total mu distortion you expect is this 2 times 10 to the negative 8. So this is kind of our holy grail of spectral distortion that we would be looking for. In terms of what this means for lambda CDM or inflationary parameters, if you will, this means that spectral distortions are sensitive to small scale power spectrum, which the numbers are here, but there's also a plot here that you can look at. So on the far left-hand side of this plot, we're seeing the largest scales in the universe, and the y-axis is the power spectrum of the primordial density perturbations. So this is the thing that inflation in principle tells you what it is. Everywhere here tells you is well measured by CMB anisotropies. So the Planck experiment, for example, puts very strong constraints, and we're very confident in saying that there is a nearly scale invariant spectrum of initial density fluctuations on these largest scales. But as you go to smaller scales, it becomes notoriously difficult to constrain or reconstruct what the actual spectrum of these fluctuations was supposed to be. And it turns out that Kobe-Virus is still the leading experimental bound in this region of parameter space. So it might look like we're pretty far from the theory line, but this has actually made a lot of people who are interested in primordial black holes very upset. Because if you want to form a primordial black hole through the standard mechanism, let's say, you need this spectrum to rise basically all the way up to this PBH line, which is very, very high. And the PBHs that you would form in the region where Kobe-Virus constrains are essentially exactly the supermassive black hole range. So people who try and describe supermassive black holes with primordial black holes often will run into problems from distortions. Now, I don't like this plot very much, even though I made it a couple of years ago, because it looks like fossil misses the sensitivity of CMB anisotropies, because this curve, if it continues to be nearly scale invariant on these scales, is below the fossil line. But this is a complicated plot to make because when you write constraint curves, you essentially usually just assume you put a delta function at every point in K space here, you calculate the distortion and you write the curve because that's the most conservative thing you can do. But spectral distortions are sensitive to the integrated amount of power on all of these scales. So if the spectrum stays nearly scale invariant, you will absolutely be able to see this spectral distortion with fossil, which is an experiment I'll describe to you in a little bit. Okay, so there's a zoo, I guess you could call it, of spectral distortion signatures you can look for. I won't go through these in much detail. I just want to highlight that the mu distortion is this kind of red curve that lives here. This is the actual what the distortion would look like itself. And the other thing I wanted to highlight were these recombination lines, which are that they have a lot of spectral features, let's say. So all of these little bumps. And the physics of this is extremely cool. So if you think about standard spectra in astrophysics, if I look at a galaxy through a sensitive spectrograph, what I am able to do is I'm able to determine exactly the elements that were around in that galaxy because of their atomic lines or molecular lines. And the universe is no different. When you go through recombination, you basically cascade through at earlier times all of the helium series, and during proper recombination at redshift of 1,000, all of the hydrogen series, and you produce these line-like features that we can in principle go and measure, and would be extremely valuable information to understand the exact microphysics that the universe was undergoing during recombination itself. So it might feel like we understand this process very well, but there are many solutions, for example, to the Hubble tension that play with recombination. And if we had a handle on this information, we would really be able to nail down what's right and what's not right. Right. Okay. So are there any questions at this point before I move on to a dark photon example? As I take a sip of water.
Just maybe a small question. So I'm just asking that typically my radio astronomer friends actually often bother about in the high L, that is the low angular separation, the Silk damping as well as the Sunyaev-Zel'dovich effect are very degenerate, right? So I'm just asking that how do you find the spectral distortion for the temperature anisotropy as well as check out the Sunyaev-Zel'dovich and the Silk damping? I mean, Sunyaev-Zel'dovich maybe you can use by radio astronomy or something like that, but the Silk damping already makes this very suppressed, right? So I'm just asking that.
So the silk damping produces mu and y type distortions, right? Depending on the redshift at which the damping on each particular scale occurs. So in fact, all of the scales that you see here are not the things that are producing the mu distortion. They're at even higher L. They're at like 10,000, 50,000, 100,000. The Sunyaev-Zel'dovich effect, there's kind of two ways to get around that. So in this zoo here, I guess that was already on the right slide, you can see that right now, the way that we detect galaxies with the Sunyaev-Zel'dovich effect is that Planck has a very special amount of tuned frequencies that will allow you to see some part of the Y-type distortion of CMB photons traveling through these clusters of hot electrons. And if you add up basically everything that Planck has seen, and you do a sky average of that, then the average Y distortion that you expect from this global SZ effect is at the level of 10 to the negative 6. But the important thing is that so Y distortions and mu distortions can be separated. I mean, they're not completely independent spectrally, but they are not degenerate either. I mean, there is, like many things, there's some degeneracy, so it's not an orthogonal basis, but there is orthogonality to it that you can project onto. And so this is why I don't talk about searching for the Y-type distortion from silk damping, because that also does exist. In fact, it's on this plot here. Because that will most likely be very difficult to see over this brighter global Sunyaev-Zel'dovich effect. But the mu distortion itself, you can still cleanly extract from the data, even after you've taken out all of the Y distortion pieces. So you should still be able to see that.
Okay, thank you very much.
No problem. Okay, so let me just do a quick foray into a paper that we had a couple of years ago on dark photons. So this will essentially be an exercise in resonant conversions. So what we considered in this spectral distortion work was a scenario in which the dark photon exists. So an additional U1 symmetry exists in nature, but it does not make up all of the dark matter. In fact, it is just kind of sitting there, perhaps empty or very sparsely populated after some high redshift freeze-in production or something. And ask the question, could you constrain this type of a model with CMB spectral distortions? And the answer turns out to be yes once you invoke some extra principles. So you can, and the Lagrangian here is given. Basically, there's a kinetic mixing term, if you haven't seen this before, that mixes the photon and the dark photon, which means that there can be level crossings that occur, similar to neutrino oscillations. So just like neutrinos can go between different flavors, photons and dark photons can transfer back and forth between each other. But in vacuum, it turns out that the conversion rate is extremely tiny, and you can't even hope to constrain dark photons in this way when you consider just these vacuum conversion rates. But thankfully, again, we live in a universe in which there is a hot, dense plasma. So what people typically do in these types of exercises is they write down I mean, thermal field theorists sometimes get a little bit frustrated with this, so I'm not looking to have a debate on that front. But people write down an effective thermal mass for the standard model photon because it is propagating through a plasma, sometimes dense, sometimes not so dense, of free charge particles. And the leading order term, at least at lower redshifts, so temperatures of a keV and below, let's say, is given by this expression, where the only thing that really varies as a function of redshift in all of these terms is the number density of free electrons. So of course, that redshifts as a function of time. So as the number density goes down, the photon's effective mass goes down. And it turns out that if you solve the equations of motion, you can find that there's a Landau-Zener resonance that occurs if the dark photon mass ends up tuned with the standard model photon mass, which goes through many orders of magnitude as the universe expands. So in terms of the range of masses, dark photon masses that you're sensitive to, the conversion redshift is basically the redshift at which you will have a large transition, in this case from the CMB photons into the dark photons, which will induce a spectral distortion. And you're sensitive essentially between 10 to the negative 4 at the high end electron volts for the dark photon mass. And then recombination basically occurs at, let's say, 10 to the negative 10 electron volts. And then you can go even lower because you can also consider resonances that take place post recombination. So you can ask the question, there's some equations down here if you want to try and follow them, but I don't have time to go into detail. You can ask the question, if there is this resonant conversion that takes place at some point during the distortion epoch, what actually happens? Do you get a large spectral distortion? And it turns out the answer is yes. So the kind of master equation that one can solve that is very simple, as a grad student, I was very happy that the mu distortion approximate equation is a very simple equation to try and solve and to play around with different models. It's basically given by this. So it's the relative rate of non-thermal energy extraction in this case, because energy is leaving the thermal bath, it's leaving the CMB photons and going into dark photons, minus 4/3 the relative entropy, so direct photon extraction from the CMB. And this second term actually matters a lot. It had not been considered before because, as I said at the beginning, the black body is always this very delicate balance between the number density of photons you have in the background and their energy composition. So when you include both of these effects at the same time, you find results like on the left. So let's just focus on the left plot for now. So again, you get very good constraints from Kobe-Firis as you go across this dark photon mass range of roughly 10 to the negative 4 to, all the way down to 10 to the negative 12 if you like. And the old results were this McDermott and Whitty from 2020, which is this red curve here. And it does not look very impressive what has changed between the blue curve, which is our result, and their curve. It's about a factor of 1.5 improvement. But there is a very crucial piece of information, which is that in reality, this second term that was always neglected completely dominates the mu distortion, which means that the mu distortion that you would predict from the dark photons is a negative mu distortion, not a positive mu distortion and not a negative mu distortion as people had found in the past. So it's never represented well in a plot like this, but the red curve and the blue curve have completely different signs. It's just that the experiments are sensitive to the amplitude of the mu distortion, for example. So this was actually a proof of concept that when you play with the Rayleigh-Jean's tail of the CMB, whether it's putting energy into it or taking energy out of it, you really need to consider the second term. Otherwise, you're going to wind up in some trouble. Yep.
Hello. Can I ask one
Sure,
question
sure.
about
Yep.
the previous slide? So here, what is the percentage of dark matter this dark photon is?
Yeah, so
dark matter here?
So for this particular model, we're assuming it's 0% of the dark matter. Okay, so this is why I have not dark matter in the top here, because the initial abundance of the dark sector is assumed to be 0 here. And that gives you, I guess, the maximum amount of energy that can transfer from one direction to the other. When the dark photon sector is populated, you have a bi-exchange where photons go to dark photons, also dark photons come to photons, and you have to compute the distortions that way as well. And it turns out that for cold dark photons, so things that are kind of clustered, not as radiation, but as just very cold in phase space, kind of localized near their mass, the entropy effect doesn't matter so much. I will show you constraints of another paper that did that back in the day. There is also kind of questions in the literature right now as to the validity of this resonant conversion process. So when you go from photon to dark photon, everything in this Landau-Zener effect that I was describing back here seems to make perfect sense and is backed up by simulations. But people have recently written a couple of papers that show that if you go the other way, so if you have dark photons that convert into the standard model photon, that the Landau-Zener resonance actually cannot be sustained for a long period of time. And so results in that direction are under question, I would say. So to answer your question, this is a very long answer to your question, but to answer your question, for us, we have initially no dark photons. After the conversion, the energy density in dark photons is something like 0.00001% of the dark matter density. So it never has any involvement in the overall evolution of the universe, the dark photons.
Yeah, thanks. But I mean, my question was, let's say if we increase it, like not
Yeah.
0.00. So in that case, I mean, I may have misunderstood. How will this graph will change in those cases? You will not see any effect, or like
No, you will see an effect, and the effect will be dependent on the relative energy density in both sectors. So if the dark photon and the CMB have roughly the same energy density, and if the spectrum of the dark photon is similar to the spectrum of the CMB, then you, in principle, could see nothing. If the dark photon is all of the dark matter, which is the other extreme example,
yeah,
then these curves typically go down. So the constraints get stronger by about 4 orders of magnitude, 3 or 4 orders of magnitude in this epsilon space. So
okay.
your constraints can get much stronger, but what I was trying to say a second ago is that the validity of the Landau-Zener approximation
Oh,
in,
yeah, that will not be okay.
yeah, that could cause problems.
Okay, thanks.
Yeah, no problem. Okay, so the other quick thing that I just want to highlight as well is that you can calculate in this model at least analytically what the spectral distortion should look like, what the shape itself should look like. And you find something very interesting. So here the black curve is the exact analytic dark photon distortion that you would expect from a single resonant conversion in at any time, not even just in the mu distortion era. This is at source. And the blue curve and the red curve are essentially the prototypical mu type and y type distortions that I showed you in one of the Messier plots at the beginning of this talk. And what you can see is that the dark photon distortion is very close to the mu distortion in general. And what this tells us is that even if you have a dark photon distortion at late times, so say post recombination, it will look like a mu distortion and it will stay looking like a mu distortion. So the thing that I said at the beginning of the talk, which is that mu distortions always encode this really primordial pre-recombination information, has to be modified slightly. And instead, I should say that if you see a mu type distortion, you either are seeing something primordial, pre-recombination, or you may be seeing a dark photon conversion. Both, I think, are extremely exciting, but yeah, it may be difficult to distinguish between those two models. So if we see a mu distortion, then I think we can start worrying about that. But we haven't seen one yet, so let's cross that bridge when we come to it. Okay, so this is what I was saying about the comparison to other probes. So basically, what we did is we flipped and increased slightly the strength of the distortions in this plot, which shows dark photon constraints for everything. And the important thing to notice here is that in these blue contours of other constraints, and also in these experimental contours, the assumption is that all of the dark matter is in dark photons. So when you have the assumption that we have, which is that the dark photon sector is initially unpopulated, then the red curves are the dominant piece. So these are actually world-leading limits on that scenario of dark photons, which is extremely cool. When you go into the stellar bounds, so these bounds come from the production of dark photons in stars, causing them to cool too quickly. These can be compared with the red bounds, and so the stellar limits in this higher mass region of dark photon masses are probably the way to go if you want to constrain this type of stuff. Yeah, and to answer your question from earlier as well, the contours that live down here are from spectral distortion constraints when the dark photon is all of the dark matter. So this is what I mean when I say you get a multiple orders of magnitude improvement on epsilon if you have all of this energy density in the dark photon sector that is allowed to convert out. But these, I would say, as of 2026, are now in question a little bit. Okay, so to finish off the rest of the talk, I just wanted to give some highlights of actual data that will be coming to this field because, as I hopefully stressed in the beginning, we haven't had any data since 1996, and people are getting desperate, and I'm getting gray hair, and so I want to spend a couple of moments. So these are all going to be European experiments. NASA isn't doing anything with this right now, unfortunately, as much as we're trying. But the European community is picking up the slack, so I really appreciate that. And maybe the Indian community will be able to get involved on some of these things as well. I know I've spoken to many Indian colleagues because I've been involved with this fossil satellite recently. Now, three of these logos I find beautiful. One of these logos I'm censoring for the moment to give you the opportunity to look away when I get to the slide because I find it truly horrific. But it's that's my personal opinion, and I will let you make your own personal opinion about it when you see it. Okay, so there are two experiments from the ground. One is called TMS, the Tenerife Microspectrometer. It's basically just a spectrometer that will be looking at the northern hemisphere from the Canary Islands in this 10 to 20 gigahertz region. The reason for this is because there's another anomaly in cosmology right now called the radiosynchrotron background, which I certainly won't go into, but seems to be an excess of radio photons above what you expect at these frequencies, and it's trying to follow up on that. But many of these BSM models, for example, produce significant excesses deep in the Rayleigh Jean's tail, and will be probed certainly by TMS itself. Uh, um, so this is the goal of them. I was in the Canary Islands in October. I saw that they were putting the experiment together, like the last touches, and they were supposed to be installing it in the observatory in January. So I expect they're taking commissioning data soon, and I'm hoping that in the next year or two there will be some results here. So I'm looking forward to that. From Italy, there's something called the Cosmic Monopole Observer, which has just been funded that will look at the end of the decade, basically, from the Antarctic in the more canonical CMB windows. So remember, the peak of the CMB is around 200 gigahertz. So this is Rayleigh Jean's tail. This is a bit of Wien tail, a bit of Rayleigh Jean's. And its goal is to really look for this strongest spectral distortion, the one that comes from this global Sunyaev-Zeldovich effect. And it should be able to see this. So this is also something that I'm very much looking forward to. Now I have to show you the logo of Doom. So if you are about to have dinner and you want to protect your stomach, this is your opportunity to look away. I'll count down 3, 2, 1. Here's the big reveal. So Bisou in French stands for kiss. And they apparently got very creative with the logo because it's a balloon kissing the sky, and it looks very beautiful and modern, but it is really not my favorite. So let's move on. So Bisou is not from the ground. It's a balloon that has been funded by the French government. Its goal, similar to Cosmo, is to look for this global Sunyaev-Zeldovich effect distortion, and it should see it at 5 sigma. The way you can really think about Bisou is it should give you a roughly 1 order of magnitude improvement in the sensitivity that Kobe fires had back in the 90s. So in the 90s, going to space got you 10 to the negative 5 in terms of the sensitivity. Now, with new technology from the Earth, or at least from the atmosphere, you can get about an order of magnitude better, but that's probably about as good as you can get. So we'll look over a wide range of frequencies. And we'll hopefully see both the Sunyaev-Zeldovich effect distortion, as well as a detection of the monopole of the cosmic infrared background, which is not actually being characterized very well so far. So that would also be very important for both spectral distortion science and galaxy science, I suppose. Right, so this is actually funded, as I said. So there's a technical flight that they're supposed to do at the end of the decade. And in principle, if the weather is good, it should fly from, I think, Sweden to northern Canada in the summer of 2031. So keep your eyes peeled. But I think something to take away from the Bisou experiment is that this will detect the global Y distortion, and that will be the first time ever that we've detected a truly global CMB spectral distortion. So this is, a brand new scientific discovery in some sense. We know it's there, but it's a discovery that will be happening, and there will be data to play with coming relatively soon. To get a little bit more long term, right now there's something called the M8 call by the European Space Agency. So this is M stands for medium class mission, which is equivalent to, I think, 500 million euros is what M means in this context. And it is what we have proposed the Fossil satellite to do. So Fossil is a space-based successor to COBE-FIRIS. It's basically just COBE-FIRIS with better technology, better understanding of the foregrounds, better analysis techniques, and will allow us to get to this primordial mu distortion that inflation predicts at the 2 to 4 sigma level. As well, you're going to see, because you have such crazy sensitivity with Fossil, you would be able to see, that Sunyaev-Zeldovich effect distortion at 100 sigma. You would be able to see relativistic corrections to the SZ effect from the distribution of electrons in these clusters. There's all kinds of very interesting science that can be done with this. So it has got a similar frequency range to BZoo. It's in space. And it's going to, if it's funded, it's going to be, this will be the transformational measurement that I'm talking about. So timelines for satellites are never very fun to talk about, so let's just rip the Band-Aid off. We already submitted a proposal about a year and a half ago now for what was called Phase 0. So there were 40 missions that submitted proposals to ESA. Of those 49 have been selected to go to Phase A. We were selected as one of the 9. And so just a month and a half ago, we finished writing a long proposal that we submitted again to ESA. And we will know in the coming months, I think end of October, early November, we should know whether or not we are one of the 5. So now there are 9. It will go to 5 missions that ESA engineers will actually look at and do feasibility studies and build prototypes of.
We have 5 minutes left.
Yeah, no problem. So this is still slightly long term, but if everything were to go perfect for spectral distortions, by the way, none of the other missions that are proposed of these final 9 are CMB or early universe missions. So you should all very much support this if you have the opportunity. There would be a launch in 2041, so you would expect some of this great data coming shortly after that. There are challenges to these types of measurements, and I don't want to gloss over them. So on the left-hand plot here, the black curve is the CMB. So this is essentially the spectrum of the CMB across the entire sky. All of these other curves are emission from other processes that essentially pollute our ability to look for CMB spectral distortions. So in order to get a sensitivity that Fossil would like to get to, for example, you need to understand each of these components exquisitely well. So this is part of the reason why the Fossil experiment would go from 50 gigahertz, which is basically here, all the way to 2 terahertz, which is here, is because if you think about the CMB, this is an exponential fall off because this is the Wien tail. Peak of the CMB is around here. The reason why you have to go to these very high frequencies is because you want to be able to resolve the peak of the monopole of this galactic dust and CIP component, which are the strongest contaminants of the spectral bands that we're searching in. So if you add all of these things together, then this gray curve, or equivalently this gray curve in this right-hand plot, is the level of essentially foregrounds that you need to understand. And I think that's the largest challenge ahead of people between now and, let's say, optimistically 2041, is leveraging not just the information that we would get from Fossil to understand these foregrounds, but also using as much information we can from all of the other great experiments that have been funded and running. All the other satellites, everything that's looking at galaxies, both near and far, also go through these foregrounds, and we can use that information to try and understand what's going on. So the sensitivity of each of the instruments that I've mentioned, so BZoo has 2 bands here, Fossil, and then Cosmo and TMS are in these different regions are listed, as well as a few of these different so here's the mu distortion, relativistic SC, the global SC, etc. So there are certainly, it's obviously a good idea to look for these things. There's so much physics wrapped up in understanding the thermalization process, but it is not something that you get for free. There is a lot of work to be done here. Now, let me just skim through this to say, this is just a compressed version of the 4 slides that I showed you a second ago. So between now and 2032, there's lots going on, and there will be lots of data for us to start looking at and constraining inflationary models and BSM models with. But the true gold mine would come basically once Fossil is funded and launched. So we are crossing our fingers for that. And then there's other more futuristic things that I will save for another time. Okay, so just to conclude, thanks for listening to me in the first place, that spectral distortions are extremely cool. I mean, I was seduced by the physics in the first place. It's one of the only ways in which you can really peer behind the veil of the cosmic microwave background and really extract information with good statistics. Because unlike gravitational waves and neutrinos, you will get a lot of data from photons. So you have good statistical power if you can get at these spectral distortions that will allow you to really nail down the exact thermal history to great precision at very high redshifts. And this is a bit of cosmological information that has been, I think, underappreciated for the last couple of decades. So I think we should be focusing at least part of our efforts on this. There are cosmological signals, there are astrophysical signals that exist in the standard model that we can certainly hunt for, that we will see with both Bizu and Cosmo, and then, of course, Fossil bringing us a treasure trove. There's tons of BSM phenomenology, so if you have a favorite dark matter model or something that lives long enough, let's say, to have some type of impact on the universe at 1 year or later, so redshift of 10 to the 6 or below, then it's very simple to do some back of the envelope estimates to see if a distortion is a way that you could characterize your model, you could constrain it, etc. And not only that, I mean, understanding inflation at different scales than what we've seen so far in the CMB anisotropies should be a major focus of the community, especially when people are getting very excited about things like primordial black holes and scalar-induced gravitational waves, for example, being an example of something that pulsar timing arrays may have seen. The power spectrum is the scalar power spectrum has so much information that bleeds into every other aspect of cosmology. And this is really, I think, the most precise way that you can measure it for orders of magnitude in K modes that I was showing earlier. So I think there's just so much great physics here, and I hope you also appreciate that as well. So thank you very much.